Hello, I present to you neural jump ordinary differential equations, which is a framework for consistent continuous time prediction and filtering. This is joint work with Calypso, Herrera and Josef Teichmann. We consider a Markovian stochastic process as defined here by the stochastic differential equation. Of this stochastic process, we have a training set of n independent paths. Each path is only observed at a random number of times, and these observation times are randomly sampled on a time interval. Our goal is to learn the L2 optimal prediction of x given the last available observation. In particular, this optimal prediction is given by the conditional expectation. One approach for this problem is to use latent variable models. The simplest are recurrent neural networks, which are usually applied to regularly sampled time series data. The latent variable h is updated after each new observation of x and constant in between. In contrast to this, neural ODEs allow updating the latent variable continuously in time by solving an ODE defined by a trainable neural network. Latent ODE and GRU-ODE base combine RNNs and neural ODEs to deal with irregularly sampled time series data. In particular, the latent variable is continuously updated by a neural ODE between observations and jumps according to a RNN when a new observation of x is made. While these models are suitable for our problem, they lack theoretical guarantees. We designed the model such that theoretical guarantees can be derived. We keep the basic architecture where the latent variable is continuously updated between observations and jumps whenever a new observation is made. However, the neural ODE takes the last observation and the needed times as additional input. Moreover, the RNN is replaced by a simple neural network, the jump NN, since we consider Markovian processes. As in all latent variable models, the output is obtained by applying another neural network, the output NN, to H. We also introduce a new objective function that allows us to prove convergence. The first part trains the jump NN by comparing the output after the jump to the observation. The second part trains the neural ODE by minimizing the distance between the output before and after the jump. Thanks to this modified architecture and the new training framework, we have the following theoretical guarantees. The output of neural jump ODE converges to the optimal prediction, which is the conditional expectation, when the number of paths and the network size is increased to infinity. This is confirmed by our empirical convergence studies. We first confirm the capabilities of neural jump ODE on synthetic datasets. It is trained using 16,000 paths and afterwards evaluated on new independent realizations with the goal to replicate the conditional expectation. Applied to data of a Heston model, the neural jump ODE nearly perfectly replicates the optimal prediction. Similar results are obtained on Black-Scholes and Ornstein-Uhlenbeck datasets. Also on more complicated datasets of a switching regime and a time-dependent drift, neural jump ODE performs very well. Besides synthetic datasets, we also apply neural jump ODE to real-world examples. On the climate forecasting problem, it performs similarly as GRU-ODE base. Moreover, it outperforms the latent ODE on the FusionNet dataset. To sum up, we introduced the neural jump ODE, which is a model for continuous time prediction and filtering. It is the first model with theoretical convergence guarantees and outperforms existing models on different empirical examples. Thank you for watching the video.